Okay, welcome back, everybody. And we're moving on. We only have a few more of these lessons to go. And then you're going to be getting a practice CET exam, a couple of them, maybe even 3. And then before you know it, you can try taking the CET if you want. And just a reminder, I have not heard from everybody as to whether or not you want to actually take the CET or not. I did hear from some of you. Thank you. I responded. The rest of you, can you please email me and let me know if your intentions are to prepare for the CET or just to complete this class with a passing grade. I need to know that because I have to start making arrangements as to registering different students. You cannot register the day of the test to take the test. It has to be done a week or 2 ahead of time. So just letting you know. You see here on our slide, I got a new toy to play with. And let me show you here. I can actually draw with a pencil for a change. It's still not really good, but it's a little bit better than me drawing with this mouse. So if I use the scribe, you can see it's a little bit better. I can even write formulas here. 1 over 2 pi square root LC. It's a little bit better, not much better, but I'm getting better with it. Okay, let's move on. So, has any of this quarter's review of the material actually helped you? Has any of this material actually helped you? Are you picking up some things that you had before and you didn't really understand it, but maybe by looking at the video or listening to me, and by the way, you can always email me if you want to try to ask me things, and I'll let you know. And have you learned anything new? Have you reviewed some material? Have you identified anything that you thought was right, but now you have it corrected because it was wrong and you're getting the right knowledge about it? It's always good to learn from your mistakes, and that's part of being a really good technician. So today's lesson is about voltage sources. Today's lesson is about voltage sources. There are some things that we're going to cover regarding voltage sources, and that actually might be a little bit more than what you've covered. For example, we're going to talk about batteries a little bit, some of the things you might find on employer exams or quizzes, or especially on the CET. We're going to talk about what a real voltage source is compared to an ideal voltage source, and then we'll talk about how a power supply converts AC into a DC voltage source and do a few calculations. So that's what we're going to cover today. Let's go ahead and move on. Okay, what are batteries? Well, batteries are a type of voltage source, and batteries use a chemical reaction to provide electrical voltage or electrical pressure. That's what batteries are. So batteries are a chemical composition of 2 plates and an electrolyte, which together create an electrical pressure. That's how all of these batteries work over here. And these batteries, there's also tons of other kinds of batteries. Now, what is the difference between a primary and a secondary cell? Well, if you got that handout that was in your notes, a primary cell is one that is used one time and then thrown away. An example of a primary cell would be batteries like this that you throw away, these D and C cells and 9-volt and AA and AAA. Those are good examples of batteries that you would use one time and throw away. Good examples of those kind of batteries would be a standard alkaline or a carbon zinc battery. Those are typically one-time use batteries. Now, a secondary cell, on the other hand, a secondary cell is a cell that can be recharged and reused over and over again. You will also see these designs in rechargeable values and rechargeable batteries. Typically, they are a type of nickel cadmium or nickel hydride. Those are the most popular kind, but not to ignore the rechargeable batteries that you have in your car. Those actually are secondary cells as well. Now, what is the difference between the mechanics of a wet cell and a dry cell? Well, wet cells like this have acid in it for the electrolyte or the chemical composition. These Dry cells have a kind of paste in there. They're not really completely dry. They're kind of pasty inside, but we call them a dry cell because if you tip them over, the electrolyte won't run out like it does in a battery like this. In a car battery, if there's a liquid in there and you tilt it on the side, the liquid can run out of the top of this battery if you tilt it. You may remember, you may not, or maybe you have a lawn tractor or an old motorcycle or something. It used to be you could take these caps off the top here and actually refill and put more water in there to replenish the water that evaporated from the acid. So that's the difference between a wet and a dry cell. Now here's an interesting aspect here, number 4. How are different kinds of chemical composition cells rated? Well, the interesting fact about this, if you look at this table over here, the interesting fact about different combinations of chemicals inside of a battery produce different voltage levels per cell. So you have a couple of plates, and you have this electrolyte in between, and when you put that chemical reaction in there, you will get a certain voltage. For example, carbon zinc and alkaline and zinc air batteries, very, very rare zinc air, those all have a cell per cell voltage of 1.5. Other types of batteries, lithium, 3 volts, nickel and cadmium, and nickel hydride, those are about 1.2 volts. So how are different kinds of chemical composition cells rated? They're rated by their volts per cell. I know that sometimes you run into this nickel-cadmium question on the CET. What is the voltage of a fully charged nickel-cadmium cell? Well, it's 1.2. You know, sometimes nickel-cadmium might come in the design like this up top here, and that nickel-cadmium is sometimes used to replace a zinc-carbon or an alkaline cell. And you'll notice here, this is only 1.2 volts, where this is 1.5. If you put 2 of these in series, you're going to get 3 volts, but 2 of these in series, you're only going to get 2.4 volts. That's why, quite often, when you use rechargeable cells to replace basic zinc or alkaline batteries, they don't seem to be quite as bright, although you can recharge them hundreds of times. So that's where the benefit lies. Okay, now, what are the volts per cell for a typical nickel-cadmium and nickel metal hydride? Well, let's take a look. It's 1.2. Those are typical rechargeable cells. They're around 1.2 volts. Okay, what about the voltage of a lead-acid cell in an automobile? Well, that's what it looks like inside. Let's go back and see. Here's a cell. Here's many cells put together to create an auto battery, but there's actually 6 cells in there. And a lead-acid has a voltage of around 2, but it's around 2.1 when it's fully charged. So each cell of a lead-acid battery would have 2 volts, or about 2.1 volts per cell. Now, what is the typical cell voltage for a zinc-carbon or alkaline battery dry cell? Well, that would be zinc-carbon or alkaline. That's a very, very popular kind of cell. Those are the throwaway batteries. Those are around 1.5 volts per cell. Now, you may be asking yourself, well, if these cells only have a certain voltage, how do we end up with batteries that are 9 volt or 6 volt or even 12 volt? Well, look, to get batteries that have a larger voltage rating, you have to combine cells in series somehow. Look at this down here. Here's a 9 volt door cell. When you open it up, you see it actually has 6 different AAA batteries placed in series. Those are all 1.5 volts each. So 6 times 1.5, that gives us the 9 volts of the total battery available at the terminals. Here's another way that they make 9 volt batteries. These are other brands. This one has the 1.5 volts stacked on top of each other. A little bit different layout, but they're 1.5 volts each. There's 6 of them in there, so that's 9 volts. Okay? So that's just showing you. If you've ever seen the inside of batteries, they actually have multiple cells to create a certain higher voltage. If you've ever looked inside of a 6 volt lantern battery, here's one right here. Typical 6 volt lantern. It's pretty large, They call it a lantern battery because sometimes you see them being used with lanterns, like when you're going camping. If you pull the top off of that, they're not all laid out the same way. But look, this actually has 4 1.5 volt double Ds in series. So 4 times 1.5, what do you get? 6 volts. It's because they're in series. Batteries, cells in series create bigger batteries. Now look up here. Up here on the upper right, you've got a 12 volt car battery. And I don't know if you've ever noticed this, but there's always 6 holes in the top where you can put water in the top of the battery. Sometimes it's sealed and you can't see it, but it's there. So you put 6 lead acid cells together in series, and you end up with a total of around 12 volts. In reality, I know back here it says that they're actually 2 volts right here, but in reality it's actually more like closer to 2.1 volts. So the real open circuit voltage of a car battery is around 12.6 volts because it's 2.1 times 6. Okay, moving on. Now we're going to talk about not just batteries and not just power supplies, but voltage sources in general, whether it's a battery or a power supply. And there's an interesting aspect about this that we need to talk about because they're going to quiz you about it on the CET exam. And that is the concept of a real voltage source compared to an ideal voltage source. Let's talk about an ideal voltage source first. Here's one right here. This is an ideal voltage source. Now, when you see an ideal voltage source drawn in a schematic, this is what you see. And what we assume about that is that because it's ideal, that the voltage here will never change on these terminals. So if this says 3 volts, it'll be 3 volts all the time, VCC of 3 volts. If it's 12 volts, it's always 12 volts. You assume it to always be the same voltage. What we find is in electricity and electronics, this is not true in the real world. In the real world, the voltage actually will change on this source when you energize the load or put more load on here. Here's a good example. In your car, you have a 12.6 volt battery or a 12 volt battery. You turn the lights on at night. The lights are fairly bright. You turn the starter. What happens to those lights? They dim a little bit because the voltage drops a little bit. This is said to be a real voltage source. Now, what causes the voltage drop in a real voltage source? Well, all voltage sources have inside of them a virtual resistance. It's not a resistor, but there's a certain amount of resistance in series with the source voltage. This is called the internal resistance of the voltage source. All voltage sources have a certain internal resistance. Ideal, we assume it to always be the voltage. In real life, anytime you load a circuit, that internal resistance will cause a little bit of a voltage drop, and therefore you will lose a little bit of voltage over here. Now, what makes them different in operation and in circuit diagram? In operation, this voltage will never change. But there's no such thing as an ideal voltage source. There's voltage sources that come close. For example, regulated power supplies come very, very close. But even they will change a little bit when they're loaded. Over here, a real voltage source has some internal resistance that causes a voltage drop before the voltage gets to the output here. So what makes them different in operation and in circuit diagram? This voltage is said to remain the same, constant. This voltage source is a real voltage source, and it will actually shift its voltage a little bit when you load it over here. That's what makes a difference in operation. Now, although technicians know that when you see an ideal voltage source, in reality it'll behave like a real voltage source. You need to know that. So even though we draw this, we assume that you know there's some internal resistance in there. Now, whenever I measure this output voltage right here with my meter, with my DMM, using a DMM by itself to check a voltage source is not a good way to check the operation of the voltage source. Here's why. Right now, is there any current flowing in this circuit? No, there's not. So when I look down here, whatever the voltage is internal, this, when I measure with the meter, I'm going to measure that voltage. The reason is there's no voltage drop internally here because there's no current flowing in that circuit. Now, the proper way to check a voltage source, a battery or a power supply, is to put a load on it. Putting a load on the positive and negative terminals actually causes current to flow in there. Now the current is flowing because, let me try my scribe here. Doggone it. I'm trying to use my new scribe. Because the voltage on internal is equal to the current flowing times the resistance internal. That gives me the voltage drop over here. And these two voltages have to add up to the source voltage. That current that flows through our internal in there will cause the voltage over here to drop. So this is why using a voltmeter by itself is a very poor way to check a voltage source. You've probably done that since you're in electronics. You get practically a dead double A or D size battery. You check it without it being loaded. It checks pretty good. You would never know it was dead. But when you turn the switch on and energize it, that you can actually get in there and check the voltage, that's when you see the voltage drop. So what is the difference between a loaded voltage source and one that is not loaded? A loaded voltage source has nothing attached to it over here. A real voltage source has a load on it. It's driving a load. There's current flowing in that circuit. So why does a real voltage source have a lower output voltage when loaded? Well, let's just repeat that. When it's not loaded, there's no voltage drop in there. When I do load it, now I'm going to lose some voltage right there on the internal resistance of the voltage source. Why? Because there is current flowing. Now, unfortunately, there's going to be a couple of questions out of 200, it's only 2%, that deal with seeing if you understand how the real voltage source works. So, look at number 5. If I was to draw a diagram of a real voltage source connected to a 10 ohm load, oh my gosh, okay, 9 volts right here, and here's a 10 ohm load, that would be this right here, and we know there's an internal resistance there. And look, it appears to be in series with the load. Now think about a simple series 2 resistor circuit. It's kind of forming a voltage divider there. What do all the volts on the resistors have to add up to? Now this word should say resistors. On the resistors, what should it add up to? Well, this voltage plus that voltage should add up to what? That voltage. So whatever voltage I get here, if I add it to the voltage here, it should add up to that. Let's do this problem. I'm going to redraw the circuit. Here's my 9 volts, and here's my 2 resistances, R internal from the real voltage source and the load. The 9 volt battery delivers a current of 0.75 amps through a 10 ohm external load which is attached to the voltage source. What is the internal resistance of the voltage source? Well, let's look at the information. What do we have? I drew the circuit, the 2 resistors representing the internal resistance and where it's connected. It's actually connected to the plus or minus. in real life, let me see if I can get this on here. This would be your positive terminal. This would be your negative terminal in real life, positive and negative. Now, that's what I need to know. I need to understand that this is not a real resistor, but it's the actual resistance caused by the inside of the voltage source itself. But it appears in series with that. So the first thing we want to find is, we know that we have the 9 volts. Here it is up here. That would be this. We know there's how many amps flowing in there, right here, 0.75. Okay. Now, how can I find the voltage on that resistance? That's my first step. That's the load. Well, I know the current, and I know the resistance. Okay. So right here, step 1. The voltage on the load would be I times R. 0.75 times the resistance. That'll give me the voltage on that resistor. So my voltage over here is how many volts? It's 7.5 volts, because 0.75 times 10 ohms is 7.5 volts. That's appearing where? Well, that's appearing right here. So on here I have 7.5 volts. Now, what do these two voltages have to add up to? This voltage and this voltage has to add up to the source voltage. So, now I have enough information to find out the voltage on our internal. Well, 9 volts is the total. This is equal to this plus that voltage. So to find this, I don't know it, but I know I have this and I know I have that. So if I subtract this from that, right here, number 2, I can find the voltage on our internal. So 9 volts minus 7.5 gives me how many volts on our internal? Well, that's quite easy. This is Kirchhoff's voltage law. My R internal, therefore, is, the voltage on that would be 1.5 volts. Okay. So now, does that look right? Because I have 7.5 here, 1.5. Does that add to 9? Yes, it does. That's my check. Now, I need to find this resistance. You see, we're working our way around. Look at the concepts they're putting together here. This is such a good question because you need to know 2 or 3 things. What did we have to know so far? Well, we know that the current times the ohms gives us the voltage. That's one thing we needed to know. The second thing was, I need to know the Kirchhoff's voltage law. This voltage plus that voltage has to add up to the total. And now I need to know one more thing. How do I find this resistance from what I already know? Well, look, I know there's 0.75 amps in that circuit. And in a series circuit, the current in one component is the same as the current in all components. So what is the current in there? The current in there has to be 0.75 amps. What is the voltage there? The voltage is 1.5 volts. So don't I have enough information to find the resistance? Think about this. I have to find R internal. R internal, okay. Well, that's going to be equal to the voltage on R internal. The voltage on, I'm apologizing, I'm using my scribe here, the voltage on R internal divided by the current through R internal, I. And look, down here, for number 3, I did that for us. R internal is equal to volts on R internal divided by the current through it. I have 1.5 volts on that component. To find the resistance of that component, I use the voltage on that component divided by 0.75. That gives us 2 ohms. So in here, this is 2 ohms. I have 2 ohms in there. Let me write that in with my scribe tool here. Okay, so I have 2 ohms. Alrighty. Is that writing a little bit better than the mouse? A little bit, not much. Okay. Alrighty, this toy's not that great of a toy after all. My new scribing toy. Now, here's my check. Very important. Did I do this problem right? Well, how can I check this? Well, I know the total resistance now, don't I? What is the total resistance here? 10 ohms plus 2 ohms. So my R total is 12 ohms. And my current should be the voltage applied divided by the resistance. And the voltage applied is 9. My total resistance is 12. And it works out to be 0.75 amps. So that's the amps they gave us before. That's how I know it's correct. Let's try this again. How about this one? This is a good car battery problem. I have a 12-volt car battery right here. It delivers 1,000 amps to a starter. Here's my starter over here. The starter has a resistance of 0.01 ohms. Find the internal resistance. Well, first draw yourself a circuit. A battery, an internal resistance, and a load. And they're in series with each other. It looks like a voltage divider. Okay, what do I know? I know that I have a 0.01 ohm resistance for the starter. Starters are a very, very heavy load. They draw a lot of current. And here I'm delivering 1,000 amps to it. So find the voltage on this resistance. I, 0.01 ohms times 1,000 amps gives me 10 volts. So how many volts are on that? That's 10. Well, I know this is 12 and this is 10. How many volts has to be on that? You should know that. 12 minus 10 gives you 2 volts. Okay, now 2 volts on there, and how much current is flowing in there? Series circuit. In the series circuit, the current's all the same. So 2 volts divided by 1,000 amps. This is the internal resistance of the battery. 0.002 ohms or 2 milliohms. More likely, this is a good problem because it shows you what happens to your car battery in the middle of dead winter when the battery's weak. You have a higher internal resistance there. So ideally, you're going to see a problem more like this on the CET. This is one just application. Also, now thinking about this, let's go back here. What would be the ideal resistance in here? How much resistance do we really want? Look at this. Here's the ideal voltage source. How much resistance is in there? How much resistance is in there? There's none. The ideal internal resistance should be 0 ohms. That means there would be no voltage drop inside of it. So when I go to use the voltage source, I will have no voltage drop. Okay. Alrighty. The next significant portion on is on power supplies as voltage sources. First of all, do you know the block diagram of a power supply? If you don't, you better. Every technician knows the block diagram of a power supply. First of all, what does the power supply system do? It takes AC and it converts it to DC. How do we do that? Well, first, you have a transformer. What is the purpose of a transformer? Do you know? Let me tell you if you don't know. The purpose of the transformer is to get the proper voltage. A transformer can change the voltage. For example, this might be 110, and we want to get a certain voltage out here, so we have to adjust the voltage. The voltage is adjusted at the transformer. We can use a transformer while it's still AC because it's the ideal device to change voltage. Transformers only work with AC, so that's why it's up front here in the system. The next block is a rectifier. What does it do? Do you know what it does? You should know. A rectifier changes the AC to DC. That is the purpose of it. The trouble with the rectifier by itself is that the rectifier, if I have 0 volts here, it actually provides a pulsating voltage coming out of it. So although it's DC and all of it's going in one direction, the electrons are kind of jerking around. So what is the purpose of the next block? Well, the next block is to filter or smooth out this pulsating DC. It makes the electron movement much smoother. It makes it smoother. In a rectifier, over here we use a transformer. Rectifiers use diodes. What do filters use? They use capacitors. They're usually parallel capacitors of some sort. All right. Now, out of the filter, we still have a little bit of ripple left. And if we were to put a load right here, the internal resistance of this system would cause the voltage to shift. We just talked about internal resistance. And therefore, quite often, but not always, a power supply will have a regulator on the output. What does a regulator do? Doesn't the regulator actually hold the voltage steady? The voltage regulator is designed to hold the voltage steady. That's what it does. So that's what the regulator does. So that's what we do. You know, voltage regulator, maybe you learn about a Zener. They also make integrated circuit regulators here. Zener's quite popular. Integrated circuit regulators are even more popular. So transformer gets the right voltage. Rectifier converts AC to DC. Filter smooths to DC. Regulator holds the voltage steady. Okay, there might be a question or two about switching power supplies. You really didn't cover switching power supplies in electronics. I don't know if you covered it in networking or not. You may or may not. But a switching power supply is designed to work with different loads on it. And the reason why they call it a switching power supply, there's a couple of reasons. It can actually switch to a higher demand or lower demand, depending on the load. So it'll switch its current or power output according to what is needed. Another reason why it's called a switching power supply is instead of using these rounded pulses here, they actually use switching pulses, which are transistors turning on and off. Okay, so you see it's turning on and off. It's switching on and off. That's another reason why it's called a switching power supply. Now, how does a switching power supply switch its load output? Well, if my load needed is very low, the width of these pulses here or here is actually made skinnier. So it has a lower average output voltage. And if I need more power, I will increase the width of the pulse. So you see here, maybe you've covered duty cycle in digital or in communication circuits. A lower percent duty cycle has more space in between. That would have a lower average DC voltage. And a higher duty cycle has a wider pulse width, and it will have higher DC voltage. Now, another way to do this is not just by making it wider, but increasing the frequency of the pulses. You may or may not have learned this, that, let me see if I can remember this properly. You may remember that the ripple, let's see here, the ripple voltage, the volts of the ripple, I don't know if you covered this in second quarter or not, that's equal to the current in the load divided by the frequency times the capacitance of the filter. And if I increase the frequency over here, I can decrease the amount of ripple. So that would be another way. Not one way for a switching power supply to get more current is to make the pulses wider. Another way is to increase the frequency of the pulses. So either way, there might be one or two questions about a switching power supply. That's what I need you to know about. I'm not going to go into it any further than that. Why are they called switching power supplies? They switch their operation to get more or less current according to the load. And also, they use a switching type wave shape instead of a round wave shape like this. It's on and off. It's called pulsating DC either way. Okay. Power supplies and loads are protected by fuses. How do you install a fuse according to the load? Well, fuses have to be installed in series with the load. Here's my voltage source, here's my load, and the fuse is in series. That's a diagram of a fuse. Fuses protect against high current situations. They are placed in series. Remember the MOV? The MOV protects against high voltage situations. How is an MOV installed? It's placed in parallel with the load. So there's two different devices. Fuses and circuit breakers protect against current damage, and MOVs, or transient suppressors as they're called sometimes, protect against overvoltage conditions. A fuse is in parallel, a fuse is in series, and an MOV is always in parallel. Okay, now, before you work on a power supply, sometimes you see, when you look at the block diagram of a power supply, right here, you see tons of large capacitors placed in parallel. These generally will be really big. 25 microfarad, 1,000 microfarad, or even 2,000 or 20,000 or 50,000 microfarad. You'd never see anything in the nanofarad or picofarad range. You'd need a lot of capacitance to actually filter in a power supply, especially if it's a very heavy or high current load. So there's a danger when you're working with capacitors. When you work on a power supply, it has a lot of large filter capacitors in there. You should discharge those. But there's a specific way to discharge them. You don't discharge them to ground with a jumper. You discharge them to ground through a suitable resistor. That provides a safe current over a period of time. So you might use maybe a 1,000 ohm resistor or 500 ohm resistor and short the capacitors to ground. And when you do that, you're discharging the capacitor. I know in lab, in electronics, if we want to discharge a cap, we just sort the leads together. You want to be careful doing something like that in a big power supply. You can get a giant spark that can startle you. You can cause a screwdriver to get welded to the terminals. In the worst case scenario, you can cause a capacitor to explode. So, when you discharge a large bank of capacitors in a power supply to ground, you don't want to make it a dead short. You want to discharge it through a suitable resistor. That question will be on the test. Okay, which two power supply types will you be tested on? Well, the two power supplies you're going to be tested on that you will see will be a full wave bridge and a half wave. These are the two that you will see. I have yet to see the two conventional diode full wave on this test. You might see it on an employee test, and the reason behind that is there's some design features about the full wave bridge that make it a little more desirable when you're engineering it. And the half wave is sometimes used for your cheaper AC power adapters. You'll see a half wave in there. But let's go ahead and look at these. In a full wave, how many DC pulses do you get for each input AC cycle? Well, look, here's one cycle between here and here. And so how many pulses do I get between here and here? Well, in a full wave, we're going to use this one for sure, and then this one is inverted and placed right here. So between here and here, how many DC pulses do I get? I get 2, because one diode makes a positive alternation, and another diode set makes a negative alternation positive. So, what is the ripple frequency of a full wave? Well, ripple frequency is how many pulses per cycle, how many pulses per second I get. If this wave right here is 60 cycle, 60 cycle is the typical frequency of the United States. And they'll test you on that. They're not going to say how many pulses per cycle you get. They're going to say what is the ripple frequency of a power supply used in the United States, a full wave power supply. Well, if I only had 1 pulse per cycle, and each cycle represents the number of times it happens per second, and in the United States you get 60 cycles per second. If I have a half wave, I'm only getting one alternation, that would be 60 pulses per second if I have 60 cycles per second. But look, in a full wave, I'm getting 2 pulses per cycle, or 2 of them for every cycle. which means that would be 60 times 2. So for a full wave, don't miss this one. If the input frequency is 60 hertz, the output would be 120 hertz for the ripple frequency. Here's another tricky one. If the input frequency is 60 hertz, what is the ripple frequency of a half-wave rectifier? Well, the inclination is to take 60 and divide it by 2, because they're saying half wave. Well, no. You're getting 1 pulse per cycle here. So if I have 60 cycles per second, I'm going to get 1 pulse per second. The ripple frequency would be equal to the input frequency. So, in general, a half wave has an input frequency that is equal to its output frequency, but a full wave has an output frequency which is double its input frequency because you're using 2 alternations per cycle. Draw the diagram of a full wave bridge rectifier and label the terminals. Here it is, right there. Okay, let's label these terminals. Let's label the terminals in this full wave rectifier. Well, what we find is that over here we have the input. Over here we have an output, it's the positive. Over here is the negative, that's an output. Just ignore this. This is referring to these 2 terminals here, not to that negative terminal. This is an input also. Quite often these inputs, because they come from a transformer, are labeled with a squiggly sign for AC coming in. Now look closely at this. What do all the diodes point towards in a full wave rectifier? Well, these are all pointing at the positive output, and these are all pointing towards the positive output. That's how you know how to draw the rectifier. All the diodes point to the positive output. They all point away to the negative output. And the AC, or input, is always in between those 2. So you can identify the positive, you can identify the negative output. The other 2 terminals will be AC. It doesn't matter which one they are because it's AC. It doesn't matter. There's no polarity there. Now, draw the full wave again with the diodes oriented differently. Sometimes you'll see it like this. Look, they'll have the positive terminal up on the top. So, and look, they're all pointing to the positive. That's how I know I'm drawing it correctly. And over here, this has to be the negative because they're all pointing away from the negative output. Where's the input? Here and here. This could be labeled AC with an AC squiggly line there, or it could be labeled just input and input. Okay. The 2 terminals of the full wave, the input terminals, are always attached to what? The 2 input terminals. Well, if you look here, look at this diagram. Here's the positive. They're pointing towards the positive. Here's the negative. That's grounded. And in the power supply, what are the 2 input terminals always attached to? They're always attached to the AC input of the rectifier or the secondary of the transformer. Almost always, you're going to have a secondary there to attach those terminals to. So the 2 input terminals of the full wave are always attached to what? Usually a transformer secondary. What are the other 2 terminals attached to? They're attached to the load. They are attached to the load right here. Here's my load. This might be a light bulb. This might be a motor. This is the positive. This is the negative. The negative here is attached to the negative over there. In this case, it's grounded. So how do you know which is the positive volt terminal, which is the common ground? They all point to the positive terminal. They all point away from the negative or the common. That's how you know. Okay, here's a schematic diagram of a simple unregulated full wave bridge rectifier. Here we go. Notice, on this rectifier, if there's a ground on there, it's only going to be in one place on the rectifier. Is there a ground here? No. Is there a ground here? No. Is there a ground here? No. There's only one place where the ground can be. It's usually the negative terminal. But there's only one ground. Well, some of you say, well, there's two grounds there. Is this attached to the rectifier? No. That's attached to the load. That ground is not on the rectifier. If on the CET you see two grounds on this rectifier someplace in here, that's bad. That is bad. Here's an example. Over here is a picture. It's hard to see, but if I look closely, all these rectifiers are pointing towards the positive output here of the power supply, and this ground is the negative right here. What is the problem with this bridge rectifier? Does it have more than one ground on it? It certainly does. There's one here and there's a ground there attached to the rectifier. That is a bad situation. That would short out this rectifier because essentially what you have there is a wire connecting this to that. That rectifier would be a dead short. So what is the problem with this diagram? That's a power supply with a full wave bridge in it, but the bridge has two grounds on it. This one, the bridge only has one ground. So watch for that. Oh no, is it the last activity already? It can't be. I want to spend the whole afternoon with you. We should make these videos about 6 hours. Do it all at one time. Let's do 3 weeks worth in one time. Make them all 6 hours long. No, of course I couldn't. That would be so boring. All right. You will need to be able to evaluate the simplest of power supplies, and that is the half-wave rectifier with a capacitive filter. Here you have one. Ignore these arrows. They're just telling you about current flow. Here's where the resistance would be located right over here. This would be your load. Okay, so here's a schematic of a fused, unregulated. Well, there's no fuse in there, but let's put a fuse in there. Let me see if I can do this with my scribe, my new toy. All right, where would the fuse be? Well, the fuse is typically right there. That would be where the fuse would be. Sometimes you'll see a lamp in there. The lamp could be here. You ignore that. All that is an indicator that the transformer is working. That might be a lamp. All right. Now, the lamp could be here. The lamp could be on the primary over here. It could be on the secondary. The lamp could even be over here. Remember, your power supply had the indicator lamps over here. They could be anywhere. The fuse could be here. The fuse could be on the output here to protect the load. Okay. But let's make the power supply attached to a load. Okay, well, I got to put a load in there. See if I can get that load in there for you. Here it is. Okay, there's a load, and we'll call that RL. Of course, good schematics have dots where the wires join. Okay. All right, there it is. Now we're going to have over here, you can see, you got to look at the details, 117 volts coming in. And what is the turns ratio of this? So coming in over here, I have 117 volts AC. And over here, I have a 10-to-1 ratio. Now, when you do these 10-to-1, all you do is you divide by the number of the ratio. We'll do this problem now. Okay, that's what the diagram looks like. How do I relate this to the blocks? Here's the transformer, block 1. Here's the rectifier, block 2. Here's the filter, block 3. There's no regulator on this. It doesn't have a fourth block. All right, before we do this, we need to review some concepts here. What units does a typical DMM or VOM read for AC? Many of you are having a problem with this. What are the units that a DMM reads? Well, a DMM will read volts AC. The DMM reads volts AC. But there's an issue here. What are other units that are exactly the same as volts AC? Volts, RMS. They mean the exact same thing. Another unit that is exactly the same thing is volts effective. Volts effective, that's another unit. Sometimes abbreviated VEFF. There's a story behind why we have these units and why they're not the same as peak or peak to peak. I'll tell that to you if you want to know it someday. Right now I don't want to bore you with that. Let's just get on with this. So when you read something on a DMM, you need to know it's volts, AC, RMS, or effective. A DMM does not read volts peak or peak to peak. Where do you read that? You read that on an oscilloscope. Okay. Now, what voltage in units would you read on the output of the transformer secondary if you used a DMM? Well, what did we say was coming into this circuit? Didn't we say that we had, into this circuit, we have 117 volts AC. All right. Now, if I read that with a meter between here and here, I would read 117 volts. Now, what was the turns ratio here? 10 to 1. 10 to 1. Now, how do I find the volts that I will read right here on the secondary? Well, I take this voltage here, and I divide it by the turns ratio here. So what is, over here, what is 117 volts divided by 10? My volts out AC, because that's what I read on the DMM, would be 11.7. That's what I would read right here with the DMM. Now, they will ask you, what might be the volts peak to peak or volts peak on that diode? You have to look and see, is it volts peak to peak or is it volts peak? Well, how do you convert this to volts peak? Because you have to go from RMS, which is volts AC, to volts peak, and then you double it for peak to peak. You'll recall we talked about the hierarchy of AC units. If I had AC units, all right, there's a hierarchy of AC units. There's the lowest value down here. Those are going to be your RMS units. And then you have your highest units here, volts peak to peak. Okay, those would be the highest units. So when I do conversions, what you should know by now is the RMS will always be the smallest value. The peak to peak will always be the largest value. So first I need to convert RMS or volts AC to volts peak, and here it is. I multiply by 1.414 to get to the next highest value, or divide by 0.707. I'm telling you now that every technician worth even the smallest skill set should be able to do these conversions off by heart. So get them down, memorize them. So I convert volts RMS to volts peak, and that would be over here. Over here, I know that my value down here I have 11.7. That's the smallest number. On it. And over here, my volts peak is what? 16.5. Okay. Now, I'm going to convert that to peak to peak. Right here, volts peak times 2 gives you about 33 volts. So over here, what is my highest voltage in my hierarchy of voltages? Well, over here, I have 33 volts. Now, does that make sense? Remember, we mentioned that the RMS is the lowest value. It's 11.7. The next highest value, volts peak, is 16.5. That makes sense. And the biggest number is 33. So these all are the same voltage. They're just specified with different units. But don't forget, volts AC is the same as RMS, is the same as effective. To get volts peak from RMS, you have to multiply by 1.414. Get volts peak to peak, you double that. All right, so watch out for this though. It might be peak or peak to peak on the secondary. If they say the voltage on the anode of the diode, they're talking about the volts on the secondary. Don't let that fool you. That is the anode there. This is the cathode. That would be a different voltage. This is the anode. All right, what kind of diodes are always used with power supplies? Well, what are the two kinds of basic diodes? Well, they're germanium and they're silicon. I think that you can ignore germanium for these exams. They're going to almost always assume they are going to be silicon. So what kind of diodes are always used? They're silicon. Silicon is a lot better with dealing with power and heat. Germaniums are very light-duty diodes. That's why we like silicon diodes for power supplies. Now, what is the voltage drop expected with a silicon diode? Well, what is it? Isn't it 0.7 volts? It's not always exactly 0.7, but for all practical purposes, we're going to use that as the second approximation or the second model to do predictions in the circuit. So what can be said? Listen to this. We got that. We got this. Here's an important topic right here, number 8. Let's talk about this for a moment. Right here. This is very, very important. If my power supply is designed properly, what we find is that here, coming into the diode, I have this AC signal, and the diode ignores this part because that's reverse bias, so this is gone. Then I have a certain volts peak coming in. And then coming out of the diode, I have to subtract the 0.7. So volts peak minus 0.7 volts will give me the volts peak out of the diode. And if this is designed correctly, coming out of the diode, I'm going to be getting these positive peaks, 0 to a positive peak. That's the volts peak out of the diode. So right here is my volts peak coming out of the diode after I subtract the 0.7. If this capacitor filter is designed properly, here's the capacitive filter right here, it will bridge together these peaks almost perfectly across the top of that. And therefore, the volts peak out of the diode in a properly designed power supply will equal the volts DC that is applied to the load. The volts DC that is applied to the load. So what can be said about the DC output voltage on the load of a properly filtered and loaded power supply? We can assume the volts out DC is going to be equal to the volts out peak out of the diode because the capacitor is properly designed to bridge these together perfectly at the peak voltage. So I have a volts peak coming into the diode, not peak to peak, volts peak. I subtract 0.7, and that gives me the volts peak that appears on the load, and that will be equal to the volts DC on the load. What would be the DC output voltage measured at the load with this DMM? Okay, so let's talk about that. I had 117 volts coming in. I have 117 volts AC coming in. Right here, I had 11.7 volts AC. And what was the volts peak to peak there? Well, the volts peak to peak was 33. And how much was 1 volt? How much was the voltage peak right in here? Well, wasn't that about 16.5 volts peak? So this is 16.5 volts peak. Now I have to subtract how many volts for this diode? 0.7. So what's left? 16.5 minus 0.7. That gives you about 15.8 volts right here. So approximately how many volts will appear on this load right here? How many volts peak will appear on that load? Well, it's going to be around 16 volts, because isn't the peaks going to be getting joined together very nicely? As we said in the previous one, these peaks will be joined together here. What's happening here is I have these volts peak. Okay. Over here, coming out, I have these positive volts peak, and they are about 15.8 volts. And so, in reality, they're joining together at the top of these perfectly. That'll be my positive DC voltage. Volts DC. I apologize. This scribe is not much better than the mouse. I might just revert to the mouse. This is okay. So really, the answer is 15.8 volts DC. But they might give you something like, what kind of answers are they going to give you? They're going to say A, 117 volts because you got 17 coming in, right? 117 volts coming in. Or they might say B, they might say 11.7 because that's the voltage from here to here. They might say 33 volts. They might have C, 16 volts. So what would be the DC output voltage? They might not even put the units on there. You have to look at the question and see, well, I need to measure volts DC. That's a giveaway that you should have that meter set to DC on the VMM. So my answer here would be 15.8 or about 16. Well, I guess the hardest part of this lesson is evaluating the half-wave power supply, because you got to do an evaluation. Let's just go back and look at that real quick. Now, over here, I drew a resistance on by accident. In reality, the resistance was already in there. I just didn't notice it immediately. But what you need to do is, for this particular problem, the first thing that you need to do is you need to know the input voltage, and it's 117 in this case, but watch out what it is. It might not be 117. You need to know the turns ratio. You need to know the volts over here, the RMS voltage coming out of the transformer dividing by the turns ratio. You need to know the volts peak coming into this diode, into the anode. You need to know that you get a 0.7 volt drop. You need to know the volts DC will be equal to the volts peak coming out of the diode because it's a properly designed power supply. So that's what you need to know to solve that. Again, this is a multifaceted problem, and it might only be worth 2 or 3 points out of 100. But it's 2 or 3 points that can really help you to pass. So let's go ahead and do the practice quiz here. The practice quiz. And here's a question from Bill Gates. Your question is Bill Gates a genius? Question one, Bill Gates is a genius, yes or no? Well, look at his answer, yes and yes, of course, stupid Microsoft. Okay, let's move on. Number one, not a very, very good picture or schematic. You might be stuck with something looking like this on a test. It's not a very good drawing. We've talked about this before. Those drawings that you're going to see on the test, they might not be that clean. But can I see anything wrong with this? Look at this and see. Look at these answers down here. Which one of these answers could possibly be the best one? Okay, let's think about this. Always use process of elimination. Is one of the bridge diode rectifiers reversed? Well, I'm looking at this. I know the positive output is where they're all pointing. Are any of these diodes pointing in the wrong direction? No. They're all pointing towards the positive. That's not a good answer. All right. Does C1 and C2 have increased filter action? My friends, that is a distractor that sounds so good. No. They do not. Here's C1 and here's C2. You can't even see what they are. These capacitors are in series. The filter action, if it increases, they would have to be increasing the capacitance. They're in series. No, it's not right. Look, I can't even see the load polarity, but let me write it in for you. This is a positive, and this is a negative. Hopefully you can see that on the real test. Well, from here, I can see the positive is feeding this load. That is not incorrect, and here's the negative over here. Okay, so load polarity is not incorrect. Well, the load ohms are not specified. Well, that's a bunch of happy BS. I don't care what the load ohms are. It don't have to be specified. It just says R over here in case you can't see it. Now, look at that bridge rectifier. What is the problem with that bridge? How many grounds should be on a bridge rectifier? We talked about this. Only one. Look, this thing has 2 grounds. There's one here, and there's one here. That thing would blow up, blow that rectifier right out if you turned that on. All right. So there you have it. The possible answer for this one would be the grounds are wrong. D. Look at the circuit below. It's connected to a 117 volt source. All right. I got 117 volts coming in, and that's going to be volts AC. That is volts RMS. Volts AC, don't be fooled by this. This is volts RMS. Now, I have 10 to 1 here. 10 to 1. What am I going to read on the secondary between here and here with the meter? Well, what does the meter read? It reads volts AC. Now, these answers all say volts AC, but watch out for the ones that have, maybe they have all the right volts, but they might have volts peak, volts AC, volts peak to peak, volts affected. You got to watch. You got to watch the units. Well, how do I find that? Well, 117 divided by 10 gives me which one of these? Don't be fooled. It's easy to say 17, but you know the correct one here is B. Okay. Look at the circuit below. Same circuit. It's connected to 117. So how many volts RMS was I getting out of the secondary? Well, I was getting 11.7. What would you read at the anode of D1? Now, you got to know the units, right? Because if it was a DMM, I would read RMS, 11.7. Okay? But what are the units here? Look at these units. Where do I read volts peak? Do I read that with a DMM? No. I read that with an oscilloscope. And look, it's not volts peak to peak. It's only volts peak. How do I convert? The anode right here, between here and here, is the same measurement between here and here as if you were using the DMM, but you're using a scope now. Well, what would be the volts peak coming into that diode? Well, 11.7 times 1.414, or divide by 0.707, your choice. What voltage did we get for that? Well, that would be 16.5. Okay, that's the volts peak right here coming into the diode right there. Right there is 16.5. Okay, now look at this one. This is the takeoff. What voltage are you going to read at point A with a DMM? This is a multiple thought question because what kind of voltage do I have to read right here at point A? What is the purpose of a power supply? To convert AC into what? Into DC. So what am I going to set my meter to read right there? I'm not going to set it for RMS AC. I'm going to set it to read DC. I know that right there on that load I'm going to read volts DC. Alrighty. Now what voltage DC am I going to read? Well, we said, let's just work through this again. I put 117 volts AC in, out of that transformer I got right here. I got 11.7 volts because it's 10 to 1 volts AC. I converted that into 16.5 volts peak right here, coming in, and coming out I have to subtract 0.7. So how many volts peak am I coming out of the diode? 16.5 minus 0.7, which is about 15.8, and that's volts peak. But what did we say earlier? That a DC power supply, DC voltage is always assumed to be approximately the volts peak coming out of the rectifier. Which one of these answers are closest to 15.8? And that's at point A in the circuit. The only one that is close is B. So your answer for that one would be B. This should shock you into something. They are not going to have exact values for answers, and they might have something close. You're just going to have to live with it. Notice it doesn't say none of the above. You got to pick one of those. All right, what is the ripple frequency of a half-wave single-phase rectifier when operated at 60 hertz? Well, your first inclination is to hear the word half and do what with this? Divide this by 2. So you might improperly answer 30. No, that's not right. Well, I get 1 pulse for every input wave. So if the input wave is 60 hertz, for a half wave I'm going to get 1 pulse per every input. The answer has to be 60. If this said full wave right here, what would be the answer? 120 if it said full wave. Which device must be installed in series for it to protect properly? Capacitors don't protect. Inductors don't protect. Zeners can protect, but they're placed in parallel. A fuse and an MOV protects. Which one of these two actually have to be placed in series? An MOV is placed in parallel. It has to be a fuse. You see what I'm doing? I'm trying to help you think through the answering of these questions, not just jumping on the first one. Everybody loves multiple choice. The problem with the multiple choice answer is it is the answer or it is not. There's nothing in between with multiple choice. Switching power supplies. What do? Are they controlled remotely? They may be. Who cares? It's a good distractor. Are they called phase inverters? Did you hear us talk about phase inverters at all yet? No. Okay, we didn't. We didn't talk anything about phase inverters. So don't answer that one. Are they always positive? Well, I don't know. Are they always negative? I don't know. What is the only good answer here that we've talked about? Remember what we've talked about. They can switch their output levels according to the load demand. That's why they're called switching power supplies. Uh-oh, look at this. Not one of these. Okay, guess what we got to do? You got to draw a circuit. You'll have a piece of paper. You'll know how to use it. Let me try my scribe again. Let me see how good of a circuit I can draw. Oh my goodness, this is awful. Let me use my mouse. Okay. Alright. Here's a DC power supply. I swear this mouse draws as good as that scribe. It has an internal resistance. Okay, here's the load it's attached to. Alrighty. Now, I have a 10 volt cell, right? So label this 10 volts. And how many amps are flowing? Well, I see this 4.5 amps. So in here is 4.5 amps flowing in the circuit. You got to be able to pick out the important information. What is the load resistance? Okay, it's 2 of. Which one of these are the load resistance? We said that one over here to the left is our internal, so this has to be the load, 2 ohms. Step 1, find the voltage on the load. 4.5 amps times 2 ohms Gosh, it looks like it's 9 volts, right? So 9 volts on the load right here. So how many volts are left over? 9 volts plus what equals 10 in the source? This has to be 1 volt on that internal resistance. How much current is flowing in that internal resistance? 4.5 amps. In the series circuit, all the current's the same. Find the resistance of this. R internal is equal to 1 volt divided by 4.5 amps. Do your math. What does that work out to be? 4.5 amps. Okay. Got my calculator here. That one's hard to do in your mind. You have to use a calculator on that one. So 1 divided by 4.5, I got 0.22. So it's going to be this one right here, 0.22. You know, another way to solve that is add these resistances individually to that resistance and multiply it by the current to get 10. That would be an alternate way. But the way I said is probably the easiest way. Okay, what is wrong with the diodes in this circuit? See if you can find out what's wrong with them. But look at the answers before you answer it. Oh, let's take a look here. Let's think about these. Is D1 reversed? A. Is D1 pointing towards the positive of the load? It sure is. Is D2 reversed? Is D2 pointing towards the load? It sure is. That's a good one. Is D4 reversed? D4 is pointing towards the positive of the load. None of those three are reversed. Is the diode ground wrong? Well, how many grounds are on this rectifier? There's only one. Yeah, there's a ground over here on the load, but that is not on the rectifier. It's on the other side of the load. There's only one ground. That's probably okay. All the diodes are pointing away from the ground. So, are any of these a problem? No, none of these. Okay, so what's the only possible answer here? None of the above. This circuit is good. It's a good circuit. Okay. Oh no. We're going back to this thing again. You're going to see 3 of these, I bet, on the CET. Look at the circuit above. It's plugged into a wall outlet. The wall outlet's providing 117 coming in. What would you read on the primary? Oh, that's a tricky one. Look. What would you read on the primary with a DMM? Well, what does a DMM read? It reads RMS, doesn't it? But what's another unit for RMS? Volt AC. Do you see what they're trying to do here? They're trying to fool you into the wrong answer. They're trying to fool you into it. Okay? You know, another answer that I've seen over here is 11.7 volts because many students just automatically jump in there and do the 10-to-1 ratio and automatically reduce it. They're not saying the secondary, they're saying the primary. You gotta read the question. So look at this circuit. It's plugged into a wall outlet and it's providing 117. What volts would you read with the DMM on the primary? Hey, on the primary I'm going to read 117 volts RMS. What's the only good answer here? The only good answer is C. Okay. Now, I don't have a slide here to tell you what you need to do for your review. It's the same thing every week. Watch for the handouts that are being printed and given to you in the Blackboard site. Look for the answer sheets. Compare your answer sheets. I know I haven't posted the answers to the quiz yet. I haven't even looked at the graded quizzes yet. I'll put them in as soon as I get out of this. And I'll put the other handouts up there so you can start looking at next week's material. But if you're seriously thinking about taking the CET, you've got to be creating a test bank. You know what I've said about the test bank. All your practice quizzes and quizzes should be in there. The ones that you know, you cross them off. Those are easy. Do not study those. The ones that you don't know, circle them or yellow them out. Once you do know the answer to those, you cross those off as well. And you focus in only on the ones you don't know. That's how you study for a certification exam. There's always a limited number of tests that you'll draw from. It's called the test bank. A limited number of questions. And if you get to know almost all of those questions and the possible answers for those and how to solve them, you will be successful. So create that test bank of tests and quizzes and practice quizzes. Okay, other than that, except for telling you that if you want to just get out of this course because you're not even interested in the CET, I know this, maybe a couple of you are, please let me know. And I think this makes up 5 or 6 weeks. This will be the 5th week. So all you need is 5 or 6 good quizzes that you've got a 6 or above on. And if you didn't, you can continue on and get a couple more and get those. And then I need you to take the, there's a final exam. It's called the program outcomes to see what you've actually learned in your courses over the last year and a half. So I'll have to give that to you, and then you'll have to give it back to me. So other than that, I guess I will talk to you later. And good luck. And if there's any questions, make sure you email me. Thank you very much.